Hi students, today we are going to connect two springs in series and we want to find the expression for the effective spring constant, the period of oscillation and the frequency of oscillation. Now in this picture you can see two springs whose individual spring constants are K1 and K2. They are connected along the y-axis. And a load M is attached at the bottom of the second spring. So it will be stretched in the downward direction along which applied force is acting. In a direction opposite to the applied force, the restoring force F will be acting in the upward direction. Okay. Similarly, in the second picture you can see two springs of spring constants K1 and K2 are connected in series along the horizontal direction. This is F applied, which acts along the positive x-axis, and the restoring force is acting along the negative x-axis. Okay. Now, in the series combination, one very important point you have to remember, you have to keep it in mind always. Any number of springs also, if they are connected in series and they are stretched by the applied force, in this case the restoring force will be the same for all the springs. You see here, the restoring force, okay, the restoring force F will be the same for both the springs, but their displacements will be different. Okay, so along the x-axis, the extension, you can call it as extension also. Okay, the extension produced in the first spring is x1 and the extension produced in the second spring is x2, but for both the springs the restoring force will be the same. Okay, so you can choose any one of these two diagrams and you can start deriving the expression. So now let us take the second picture. Okay, I am going to derive the expression for the second picture only. Okay, I said that the restoring force F, okay, for the first spring. So for the first spring, I will write the restoring force F is equal to minus K1 times x1. Okay, students. So F is equal to minus Kx is the general format. Therefore, what is x1 alone is equal to minus of F divided by K1. Okay. Now, for the second spring, I will write an expression for the second spring. A similar equation if I write means, since the restoring force is the same, left hand side is the same. So F must be equal to minus K2 times x2. Therefore, what is x2 alone equal to? Therefore, x2 is now equal to minus of F divided by K2. So, these are the extensions produced in the first spring and the second springs respectively. Therefore, what is the net extension produced? The net extension produced is x is equal to minus F by K1 minus F by K2, or x is equal to minus of F is common in both terms. So I will take minus F into 1 by K1. Minus is taken outside. Therefore, I can write here as 1 by K1 plus 1 by K2. So this is the required equation number 1. Okay. So the net extension produced in the combination of the two springs will be equal to what? X is equal to minus of F times 1 by K1 plus 1 by K2. Okay. Now the general expression, okay, from the general expression, suppose if the two springs are replaced by a single spring for the same restoring force, then the extension produced okay, or the restoring force F must be equal to minus of K combination, that is K series times the extension produced. So I am going to replace these two springs by a single spring which produces this net extension x for the same restoring force. Means then what should be the spring constant of that effective spring? It is denoted by the symbol K, S. Okay, children. So I will take x. Therefore, what is x now equal to? Minus F divided by K series. So this will be our equation number 2. Okay. So from the first equation, what is x equal to? Minus F into 1 by K1 plus 1 by K2. This is when two springs are connected in series. Suppose if these two springs are replaced by a single spring of a spring constant Ks, then x is also equal to minus F divided by Ks. So the left hand sides are the same. So I am going to equate these two equations. So equating 1 and 2. The right hand sides of equations 1 and 2 are equated. So I will write minus F divided by Ks is equal to minus F into 1 by K1 plus 1 by K2. So minus F get cancelled, or we can write 1 by K series is equal to 1 by K1 plus 1 by K2. So this is a reciprocal of the effective spring constant is equal to the sum of the reciprocals of the individual springs. Is it not? So this also can be written as what? If you take LCM, K1 plus K2 divided by K1 K2. So I will write this as equation 3. Or the same I can also write taking the reciprocal K series is now equal to what? K series will be equal to K1 into K2 divided by K1 plus K2. So in this format also we can write the effective spring constant. Okay students, now look at the equation 3. For two springs we have written two terms on the right hand side. Is it not? Suppose for n springs, okay, for n number of springs, what will be the expression for 1 by Ks will be equal to 1 by K1 plus 1 by K2 etc. up to last term will be what? 1 by Kn. N number of terms will be added up. So here you can write 1 by K series is equal to sigma. When you sum up n number of terms, mathematically the symbol sigma can be used, is it not? So sigma 1 divided by Ki, where I is running from 1 to n. Is it not? Suppose you take, if K1 is equal to K2 is equal to up to Kn. If all are identical springs, identical means their spring constants are same, okay, then what will be 1 by Ks will be equal to, so 1 by K plus 1 by K up to what? Last term is also 1 by K. So this will be equal to what? N times. So n by K, or what is the K series now is equal to K divided by n. So this is equation 5. Okay students, have you understood? K series is now equal to what? K by n, where K is the spring constant of only one spring. This is for n number of identical springs. So we must come to know that when n number of springs which are identical and having the same spring constant are connected in series, then the effective spring constant is reduced by a factor n. Okay, this equation is very important for competitive exams. Okay students, now let us come back to the combination of two springs in series. So in this case, what will be the period of oscillation of the system consisting of two springs? So the period of oscillation T, okay, is given by, you must remember the general expression, okay, that is period T is equal to 2 pi into square root of m divided by k. And here instead of k, I should substitute what? K series, ks. This equation number 4. So what is ks equal to? K1 into k2 by k1 plus k2, is it not? So if I substitute here, it will become 2 pi into square root of m into k1 plus k2 divided by square root, okay, inside k1, k2. So this is our equation number 6. Okay children, see, ks is substituted. So first k1, k2 product will remain in the denominator and the sum term will be shifted to the numerator. Okay, now the frequency of oscillation is given by the reciprocal of the time period. So f must be equal to now 1 by period. This is equal to 1 by 2 pi into square root of. Now the product k1, k2 will be shifted to the numerator. So here it is k1 into k2 divided by m into k1, okay, plus k2. And this will be our equation number 7. So my dear students, here you must remember the equations number 5, 6 and 7 thoroughly always for that is writing the competitive examinations. So equation number 6 and 7 usual expressions we have derived already for so many cases like the simple pendulum, okay, vertical and horizontal cases and all. Like that here also the period of oscillation and the frequency of oscillation anytime you have to write and practice. So once again I am repeating, whenever the springs are connected in a series either along the x-axis or along the y-axis, the restoring force will be the same, but the individual displacements are different. So now itself we can guess what may be the condition for when the springs are connected in parallel. In parallel combination, the restoring forces will be different, but the individual displacements will be the same. Okay, so I will meet you in the next topic, parallel combination of springs. I hope you must have understood this fine. Okay, well.